Welcome to today's session. In this video, we'll tackle problem number 436, titled Find Right Interval. This is a fascinating challenge that combines sorting and searching techniques, often seen in competitive programming and technical interviews. Let's dive in and break it down step by step. In this problem, we are working with an array of intervals, where each interval is defined by a start and an end point. Specifically, the ith interval is represented as start_i, end_i. The goal is to determine, for each interval, the index of the smallest interval that starts at a point greater than or equal to the end of the current interval. If no such interval exists, we will return -1 for that interval. The output will be an array where each element corresponds to the index of the right interval for the respective input interval. For the input, we are given a list of up to 20,000 intervals, with each interval containing exactly two values, the start and end points. These values can range from -10⁻6 to 10⁻6. The output is an array of integers, where each value is either the index of the right interval or -1 if no right interval exists. If a right interval does not exist for a given interval, the output will be -1 for that interval. Let's explore this with a few examples. In the first example, we have an input of intervals equals 1, 2. Since there is only one interval in the array, there are no other intervals that can satisfy the condition where the start of another interval is greater than or equal to the end of this one. Therefore, the result is -1. In the second example, the input is intervals equals 3, 4, 2, 3, 1, 2. Here, the output for the second example is -1, 0, 1. Let's break it down. For the first interval, 3, 4, there is no other interval that starts at or after end equals 4, so its result is -1. For the second interval, 2, 3, the smallest interval that starts at or after end equals 3 is 3, 4, which is at index 0. Finally, for the third interval, 1, 2, the smallest interval that starts at or after end equals 2 is 2, 3, which is at index 1. In another example, the input intervals equals 1, 4, 2, 3, 3, 4, produces an output of -1, 2, -1. Looking at this example in more detail, for the first interval, 1, 4, there is no interval starting at or after end equals 4, so the result is -1. For the second interval, 2, 3, the smallest interval that starts at or after end equals 3 is 3, 4, which is at index 2. Finally, for the third interval, 3, 4, there is no interval starting at or after end equals 4, so the result is again -1. Moving on to the constraints, the number of intervals n can be as large as 20,000, and the values of start and end for each interval can range from -10⁻6 to 10⁻6. The intervals may not be sorted, so the solution must handle this efficiently. Some edge cases to consider include arrays with a single interval, scenarios where no valid right interval exists, overlapping intervals, and ensuring the solution can handle the upper limit of 20,000 intervals efficiently. To tackle the problem of finding the right interval, the first approach we can consider is the brute force method. The intuition here is straightforward. For each interval I, we loop through all other intervals to locate the smallest index j such that the start of interval j is greater than or equal to the end of interval I. This involves a nested loop where, for every interval, we compare its end value with the start values of all other intervals, keeping track of the smallest valid index. If no such interval exists, we return -1 for that particular case. While this approach is simple to implement, it has a time complexity of n², due to the nested iteration over all intervals. Additionally, the space complexity is 1, since we don't use any extra data structures. However, this quadratic time complexity makes the brute force method impractical for large inputs, especially when the number of intervals can reach up to 10,000, as the performance degrades significantly with input size. Now, to improve the efficiency of our solution, we can utilize an optimized approach that combines sorting and binary search. The key observation is that, instead of iterating through all intervals for each input, we can sort the intervals by their start values. This allows us to efficiently locate the smallest start_j that satisfies the condition start_j equals end_i using binary search. Here's the step-by-step breakdown. First, we store the original indices of the intervals since sorting will disrupt their order. Then, we sort the intervals based on their start values. For each interval I, we perform a binary search to find the first interval j whose start value meets the condition. Finally, we record the index of this interval or -1 if no such interval is found. The sorting step takes O, n log n, and the binary search for each interval takes O, log n, resulting in an overall time complexity of O, n log n. Space complexity is O, n, as we need to store the original indices and some auxiliary data. This optimized binary search approach offers significant advantages over the brute force method. The most notable benefit is its ability to handle large input sizes efficiently, thanks to the O, n log n, time complexity. While there is a minor trade-off in terms of space usage due to the need for storing indices and maintaining the original order, this is a reasonable compromise for the substantial performance gain. What makes this strategy particularly effective is the insight that sorting the intervals by their start values transforms the problem into a series of quick log-time searches. This eliminates the need for a nested loop entirely, making the solution both elegant and scalable. When comparing this approach with alternatives, the brute force method stands out as simpler but far less efficient for larger datasets. In contrast, the binary search approach strikes the right balance between implementation complexity and computational efficiency, making it the most practical choice for this problem. Despite the added pre-processing step of sorting and the use of auxiliary space, the binary search-based solution is robust and scalable. These minor trade-offs are more than compensated for by the dramatic improvement in performance, particularly for large input sizes. Another advantage of this approach is its ability to handle edge cases gracefully, such as when no valid j exists for a given interval. Ultimately, the binary search optimization is the preferred strategy for solving this problem. It is both efficient and well-suited for real-world scenarios where performance matters. By reducing the problem to a combination of sorting and quick searches, we achieve a solution that is not only faster but also more elegant and reliable, making it the optimal choice for this task. To solve this problem, we are tasked with finding, for each interval in the input, the smallest index of another interval whose start value is greater than or equal to the end value of the current interval. If no such interval exists, we will return -1 for that specific interval. The brute force solution begins by taking the list of intervals as input and initializing an empty result list to store the indices. The idea is to iterate through each interval in the list and, for each one, search for the smallest valid index in the remaining intervals. This process starts with an outer loop where we extract the end value of the current interval, which serves as the reference for our comparison in the inner loop. In the inner loop, we compare the end value of the current interval with the start values of all other intervals. For every interval, we check if its start value is greater than or equal to the end value of the current interval. If this condition is satisfied, we keep track of both the index and the start value of the interval. We then compare these values to find the smallest valid index that meets the condition. After processing all intervals for a specific outer loop iteration, we append the smallest valid index to the result list. If no valid index is found, we append -1 instead. Once all intervals have been processed, the result list containing the indices is returned as the output. The brute force approach involves a nested loop structure where the outer loop iterates through all intervals and the inner loop performs a comparison for each one. This results in a time complexity of O, n squared, where n is the total number of intervals. While this method is computationally expensive, it ensures that no valid interval is overlooked since every possible pair is checked. It's also important to consider edge cases, such as when the input list is empty, where the output should be an empty list. If no valid index exists for a specific interval, the result should include -1 for that interval. In cases where multiple indices are valid, we always choose the one corresponding to the smallest start value. To implement the solution, we store the input intervals in a list or similar data structure, such as a list of lists or tuples. We also initialize an empty result list to collect the indices for each interval. For instance, consider the example input where the intervals are 1, 2, 2, 3, 3, 4. This example will help us understand how the nested loop processes each interval and determines the corresponding indices for the result list. Let's walk through the example step by step. Starting with the outer loop for I equals 0, the interval is 1, 2, with an end value of 2. In the inner loop, we compare this end value with the start values of all intervals. For interval j equals 0, the start value is 1, which is less than 2, so it's not valid. For interval j equals 1, the start value is 2, which satisfies the condition, so we update the smallest valid index to 1. For interval j equals 2, the start value is 3, which is valid but does not result in a smaller index than j equals 1. Thus, we append 1 to the result list. Next, for I equals 1 with interval 2, 3, the end value is 3. Comparing against other intervals, only the start value of interval j equals 2 is valid, so we append 2 to the result list. For the final outer loop iteration, I equals 2 corresponds to the interval 3, 4, with an end value of 4. In the inner loop, we compare this value with the start values of all intervals but find that none of them satisfy the condition. Since no valid index is found, we append -1 to the result list. After all iterations, the final result list is 1, 2, -1. To optimize this approach, we can use sorting and binary search. By sorting the intervals based on their start values, we can efficiently locate the smallest valid index using binary search, reducing the time complexity from O(n²) to O(n log n). In summary, the brute force method provides a simple yet computationally expensive solution for this problem. It ensures correctness by checking all possible pairs of intervals but struggles with efficiency for larger inputs. By leveraging sorting and binary search, we can significantly improve the algorithm's performance, making it more scalable for larger datasets. These optimizations are key to reducing the computational burden while maintaining the accuracy of the solution. This is the solution for LeetCode problem number 436, find right interval. The goal is to find the smallest index j for each interval I such that the start of interval j is greater than or equal to the end of interval I. If no such index exists, return -1. To solve this efficiently, we use a combination of a dictionary, sorting, and binary search. 1. Mapping start points to indices *. The first step is to create a dictionary that maps each interval's start point to its index in the original input. This helps us quickly retrieve the index of an interval after sorting. 2. Sorting start points *. Next, we extract all the start points from the intervals and sort them in ascending order. Sorting enables us to use binary search for efficiently finding the required intervals. 3. Binary search for each interval *. For every interval, we use the bisect_left function to find the smallest start point that is greater than or equal to the current interval's end. This operation is performed in logarithmic time, making the solution efficient. 4. Result construction *. If the binary search finds a valid start point, we use the dictionary to retrieve the original index of the corresponding interval. Otherwise, we append -1 to the result. The overall time complexity of the solution is O(n log n), where n is the number of intervals. This comes from the sorting step and the binary search for each interval. The space complexity is O(n), due to the dictionary and the sorted list. This approach ensures an optimal and elegant solution to the problem, leveraging sorting and binary search for efficiency. Here, we start by defining the find-right interval method, which takes a 2D array of intervals as input. In the first step, we create a map called start_to_index to store each interval's start point as the key and its original index as the value. This mapping will help us efficiently retrieve the index later. We then populate this map using a loop that iterates through all the intervals. Next, we extract all the start points into an array called starts. These start points are then sorted in ascending order to prepare for binary search, which is crucial for optimizing our solution. After initializing an empty result array to store the indices of the right intervals, we begin iterating over each interval. For every interval, we focus on its endpoint and use binary search to find the smallest start point that is greater than or equal to this endpoint. This is done using a helper function called binary search, which we will discuss shortly. Once we find this start point, we use the start_to_index map to retrieve the original index of the corresponding interval and store it in the result array. If no valid interval is found during the binary search, we store -1 in the result array to indicate that there is no right interval for the current interval. Finally, after processing all intervals, we return the result array containing the indices of the right intervals. Now let's look at the binary search helper method. This method is designed to perform a binary search on the sorted starts array to locate the smallest start point that is greater than or equal to the given target. we initialize two pointers, left and right, to represent the search boundaries. In each iteration, we calculate the middle index and check if the value at mid is less than the target. If it is, we move the left pointer to mid plus 1. Otherwise, we adjust the right pointer to mid 1. This process continues until the pointers converge, at which point left will point to the desired position. The method then returns left as the index of the smallest valid start point. This binary search approach ensures that the solution is both efficient and scalable, even for larger input sizes. To solve this problem, we need to determine the right interval for each interval in the given list. A right interval for an interval I is another interval j where the starting point of j is greater than or equal to the ending point of I, and among all such intervals, the one with the smallest starting point is chosen. If no such interval exists, we return -1 for that interval. For example, consider the intervals 1, 2, 2, 3, 3, 4. First, we map the starting point of each interval to its original index so that we can easily track the intervals later. This gives us the dictionary, 1 o'clock, 2, 1, 3, 2. Next, we extract all the starting points from the intervals and sort them, resulting in the sorted list, 1, 2, 3. With this setup, we can now process each interval to find its right interval. For the interval 1, 2, its ending point is 2. Using binary search, we find the smallest starting point in the sorted list that is greater than or equal to 2. The bisect_left function gives us the index 1, where the starting point is 2. This maps to the original index 1, so the result for this interval is 1. For the interval 2, 3, its ending point is 3. Again, using binary search, we find the smallest starting point greater than or equal to 3. The bisect_left function gives us the index 2, where the starting point is 3. This maps to the original index 2, so the result for this interval is 2. Finally, for the interval 3, 4, its ending point is 4. Using binary search, we attempt to find a starting point greater than or equal to 4, but bisect_left returns the index 3, which is out of bounds. This means no valid interval exists, so the result for this interval is -1. The final result for the first example is 1, 2, -1. Now, let's take another example with intervals 3, 4, 2, 3, 1, 2. First, we map the start of each interval to its original index, resulting in the dictionary 3 o'clock, 2, 1, 1, 2. Next, we extract and sort the starting points, giving us the sorted list 1, 2, 3. With this setup, we process each interval to find its right interval. Starting with the interval 3, 4, its ending point is 4. For the interval 3, 4, we perform binary search to find the smallest starting point greater than or equal to 4. The bisect_left function returns the index 3, which is out of bounds, so no valid interval exists, and the result is -1. For the interval 2, 3, its ending point is 3. Using binary search, we find the smallest starting point greater than or equal to 3. The bisect_left function returns the index 2, where the starting point is 3. This maps to the original index 0, so the result for this interval is 0. For the interval 1, 2, its ending point is 2. Using binary search, we find the smallest starting point greater than or equal to 2. The bisect_left function returns the index 1, where the starting point is 2. This maps to the original index 1, so the result for this interval is 1. The final output for this example is -1, 0, 1. Now, consider another example with intervals 1, 4, 2, 3, 3, 5. For this example, the first step is to map the start of each interval to its original index, resulting in the dictionary 1 o'clock, 2, 1, 3, 2. Next, we extract and sort the starting points, which gives us the sorted list 1, 2, 3. Now we process each interval. For the interval 1, 4, its ending point is 4. Using binary search, we try to find the smallest starting point greater than or equal to 4. The bisect_left function returns the index 3, which is out of bounds. This means no valid interval exists, so the result for this interval is -1. For the interval 2, 3, its ending point is 3. For the interval 2, 3, we perform binary search to find the smallest starting point greater than or equal to 3. The bisect_left function returns the index 2, where the starting point is 3. This maps to the original index 2, so the result for this interval is 2. For the interval 3, 5, its ending point is 5. Using binary search, we attempt to find a starting point greater than or equal to 5, but the bisect_left function returns the index 3, which is out of bounds. This means no valid interval exists, so the result for this interval is -1. The final output for this example is -1, 2, -1. To analyze the time complexity of this solution, we start by identifying the key steps involved. First, we iterate through the list of intervals to create a dictionary that maps each interval's start point to its original index. This requires n time since we process each interval once. Next, we extract the start points from the dictionary and sort them. Sorting the list involves a time complexity of n*log n, as sorting operations typically dominate in such cases. Finally, for each interval, we perform a binary search on the sorted list of start points using the bisect_left function. Each binary search takes log n, and since this is repeated for all intervals, the total time complexity for this step becomes n*log n. When we combine these steps, the sorting operation, which is n*log n, is the dominant term. Therefore, the overall time complexity of the solution is n*log n. Now let's look at the space complexity of the solution. The first major component is the start_to_index dictionary, which maps the start of each interval to its original index. Since the dictionary contains one entry per interval, it consumes n space. The next component is the starts list, which stores all the start points of the intervals. With n intervals, this list also requires n space. Finally, the result list, which holds the output for each interval, similarly requires n space since it has one entry for each input interval. Importantly, the binary search operation via bisect_left does not require any additional memory, as it operates directly on the sorted list. When we combine these components, the total space complexity of the solution is n, which is optimal given the need to store the input and output data. Let's compare this optimized approach to a naive solution to better understand the improvements. In a brute force approach, we would check each interval against every other interval to find the right interval. This would involve nested loops, leading to a time complexity of n squared, as each interval would require scanning all other intervals. The space complexity of the naive approach would still be n to store the result. In contrast, the optimized solution leverages sorting and binary search to reduce the time complexity to n*log n, which is a significant improvement over n squared. The space complexity remains n, which is already optimal. Additionally, this solution achieves consistent performance across all cases. The sorting step dominates, making the time complexity consistently n*log n, regardless of the input structure. The binary search ensures efficient lookups for each interval, further contributing to the algorithm's overall efficiency. To justify the big O complexity, we note that the sorting step is the most computationally expensive part of the algorithm. Sorting the starts list requires n*log n operations, which is asymptotically larger than the n time needed to create the dictionary or the log n time per binary search. Since each binary search is performed once for every interval, the total time for all search operations is n*log n, matching the sorting step's complexity. Therefore, the overall time complexity is dominated by sorting, making it n*log n. This is the most efficient approach for this problem, as sorting allows us to reduce the repeated comparisons seen in the naive approach, and binary search ensures that the lookup process for the right interval remains highly efficient. When working with interval problems, there are several common mistakes to be aware of. The first is forgetting to sort the intervals, either by their start or end times. Sorting is critical because it can significantly reduce the complexity of your solution. For example, instead of an n squared approach with nested loops, sorting allows you to use n log n strategies like merging or binary search. This is particularly important for problems that involve efficient traversal or comparisons between intervals. Another frequent mistake is relying on nested loops to check overlap conditions. While this might seem straightforward, it results in quadratic complexity, which is often too slow for larger input sizes. Instead, more efficient approaches, such as using a stack, priority queue, or binary search, can solve these problems in linear or logarithmic time after sorting. Finally, don't overlook edge cases. Handling scenarios like an empty list or a single interval is crucial because they can cause runtime errors if not addressed properly. These situations are often intentionally included in tests to ensure your solution is robust. Another pitfall to watch out for is making off-by-one errors during binary search. Binary search is a powerful tool for interval problems, but it's easy to mismanage the bounds, which can lead to skipping valid intervals or even accessing indices out of range. To avoid this, carefully validate your implementation and think through the logic of your index adjustments. Additionally, be mindful of space usage. While solving interval problems, it's common to accidentally duplicate intervals or create large auxiliary structures. This can unnecessarily increase space complexity, which is problematic if the problem constraints require minimal extra space. Striving for efficient space usage, such as in-place operations, can make your solution both cleaner and more performant. To excel in interviews involving interval problems, there are a few key strategies to keep in mind. First, recognize common patterns. Many of these problems revolve around sorting the intervals and applying data structures like heaps, stacks, or binary search for efficient processing. Spotting these patterns early can save valuable time during the problem-solving process. Second, clearly communicate the trade-offs of your chosen approach. For instance, explain why sorting combined with binary search is more efficient than using a naive brute force method. Third, pay special attention to edge cases. Interviewers often test scenarios like overlapping intervals, intervals that just touch at the edges, or even an empty input list. Finally, always be aware of your solution's time and space complexity. Aim for an O(n log n) solution whenever possible, as this level of efficiency is typically expected for interval problems. There are several related problems that share similar patterns and can help reinforce your understanding of interval-based solutions. For example, LeetCode 56, Merge Intervals, focuses on combining overlapping intervals, which is a classic problem solved efficiently through sorting. LeetCode 57, Insert Interval, introduces the challenge of inserting a new interval into a sorted list, requiring careful merging logic. LeetCode 435, Non-Overlapping Intervals, uses a greedy algorithm to find the minimum number of intervals to remove in order to eliminate overlaps. Lastly, LeetCode 452, Minimum Number of Arrows to Burst Balloons, applies a similar greedy approach but shifts the focus to minimizing actions required to cover all intervals. Each of these problems highlights different facets of interval manipulation and provides opportunities to practice alternative approaches. For instance, while the brute force approach is simple to implement and great for understanding the problem, its O(n squared) complexity makes it unsuitable for larger inputs. A sorting plus greedy strategy, on the other hand, is often optimal, achieving O(n log n) complexity but requiring careful implementation during the merging or decision-making process. For more advanced scenarios, you might consider alternative approaches like sorting combined with binary search or using a heap or priority queue. Sorting plus binary search can further reduce complexity in cases where you need to find the next interval or a specific condition efficiently. However, this method is more complex to implement and requires extra attention to avoid common pitfalls like off-by-one errors. Another option is the heap or priority queue approach, which is particularly useful for dynamic interval problems where updates need to be processed in real time. While this method offers flexibility, it comes with higher space complexity due to the auxiliary data structures involved. Understanding these trade-offs and choosing the right approach based on the problem constraints is crucial for crafting an optimal solution. Great job following along. Today we covered the find right interval problem, explored sorting and binary search techniques, and discussed their efficiency. Remember, mastering these concepts will help you tackle similar problems with confidence. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!